So now we want to start looking at a series. So a series would be a sum of the individual terms that make up a sequence. So if we have a sequence, a sub n, and it could be a finite sequence or it could be an infinite sequence. So let's just consider the sequence of a sub n from n equals 1 to n equals 5, for example. Then the corresponding series for this sequence would be the sum from n equals 1 to 5 of a sub n, which would be a1 plus a2 plus a3 plus a4 plus a5. Now, when it's a finite series, this is really nothing special, right? This is just adding up a bunch of numbers, and we can do that, even with the most complicated of functions pretty easily. But what about if we want to add an infinite number of terms? Okay, so we've already kind of seen this in the context of the integral, where with the improper integral, where we are integrating over a infinite space, it's kind of like, adding up an infinite number of terms. And the integral itself, even a finite integral, is like adding up an infinite number of terms, right? Because we're adding up an infinite number of those rectangles. So now we want to kind of extend this to just looking at a series by itself. How do we deal with things like the series of n equals 1 to infinity of a sub n? Okay. And it's going to be related to the work that we did on series, which was namely we want to look at, of sequences. Namely, we want to look at the sequence, and we want to see if there is some limit of the sequence, right? If it converges as n goes to infinity. But the sequence that is on the inside here, that converging is not going to be enough to tell us that the series itself converges. So a good example of this, and we'll get into this example later, but I just want to use it as kind of like the motivating example here, is that the sum of 1 over n from n equals 1 to infinity. So if you remember, this is 1 plus 1/2 plus 1/3, etc. This is not convergent. Okay, so this is a divergent series. Even though the sequence itself, right, the sequence itself converges to 0. But that's not enough for us to say that if we add all the terms together now, that also converges. So even though the terms themselves are eventually going to 0, the series itself does not actually converge. But something like this, n equals 1 to infinity of 1 over n squared. So we just changed it a little bit. We just changed the power on the bottom here. This is convergent. Okay, so this is less than infinity. This is another way to write that it's convergent. So, on the surface, these don't really seem too much different. Both of them, the sequences are going to 0, right? So we just kind of logically following it, it would seem like maybe they would both be convergent, but our intuition often fails us when we're going to infinity. So we're going to need to do a little more work to establish exactly how we can determine whether a series is convergent or not. And it's not. So there's a lot of different tests that we're going to go over in order to determine whether a series is convergent or divergent. And determining if it's convergent or divergent is one thing, but then we're often also concerned about what number does it actually converge to. So we'll look at some techniques to do that. A lot of the tests will just tell us if it's convergent or divergent and won't necessarily tell us exactly what number it's converging to. But we don't always need that. The reason we even need this in the first place is a lot of times, a lot of theorems are dependent on the series of terms being convergent. It's not necessarily, and it doesn't necessarily matter what the number actually is that it converges to. So one way that we can do this is by looking at what's called the partial sums of a series. So let's take, as an example here, we can take n equals 1 to infinity of 1 over n times n plus 1. Okay. So this one's pretty similar to the series of 1 over n squared, which, shouldn't be too surprising because this is just, it's close to n squared, except one of the terms is n plus 1, right? So we would expect it to converge. So typically when series are like pretty close to each other, we typically would expect them to behave the same way, and we'll kind of, look at that a little bit later. But let's just think about what would happen here if we want to look at what we call the partial sum. So this would be, okay, what is the sum? So if we just forget about the infinite series for a second, let's consider the series, and we're going to call this S sub k of n equals 1 to k of 1 over n times n plus 1. So this means that if we were to look at S1, for example, this would be just the first term. Okay, so S sub k is the sum of the first k terms. So S1 would just be the sum of the first term, which would be 1 over 1 times 2, so 1/2. Okay. S2 would be the sum of the first two terms. So it would be 1/2 plus whatever the second term is, which is 1 over 2 times 3, which is 1/6. So this is 1/2 plus 1/6. This is going to come out to 2/3. S3 then is going to be 2/3 plus 1 over 3 times 4, so 1/12. This is going to come out to 3/4. Okay, and you can keep doing this. You can keep looking for the pattern here. So you want to look at these numbers and try to determine if there's a pattern. These partial sums themselves will form a sequence. Okay, so we want to see, okay, does this sequence converge to anything? And if it does, then that tells us what the series converges to. Okay, I'll write this down in a minute as a definition, but we just want to think about what we're doing first. So we're kind of taking the series and now we're viewing it as a sequence by looking at the sequence of the sum of the first k terms. So the sum of the first term, the sum of the first two terms, the sum of the first three terms, and that itself forms a sequence. And then we can look for the limit of that sequence. So in this case, this is forming the sequence of n over n plus 1, right? So we just have the bottom number in each of these terms is 1 more than the top number, and it does start at, would start at n equals 1. So we have the sequence n over n plus 1. So we go ahead and take the limit as n goes to infinity, and we know that this goes to 1. Right? So this tells us that the infinite sum of this is equal to 1. So this is kind of the ideal way to find whether or not an infinite series converges, because this tells us exactly what number it converges to. Now, it's not always simple to do. You can imagine this can get very complicated, and it might not form a very good pattern. So it might not be a feasible way to do it, but if we can, this would be the ideal way to do it. We'll look at another basic example here. Okay. What if we just look at -1 to the n? Okay. So if we look at the partial sums of this, the sum of the first term would be -1. sum of the first two terms would be now -1 plus 1, which would be 0. The sum of the first three terms then would be 0 plus a -1. So we'd be back at -1, etc. So the sequence here of the partial sums is alternating between -1 and 0. It's a little bit hard to write it out, so we might just write down the numbers here. But the important thing is that it's clear that this sequence is not converging to anything, right? So we would say that this is divergent. Okay, it can't be converging to anything if it's constantly alternating between these two numbers forever. So just to write it down formally here, then if the sequence of partial sums, S sub k converges to a number S, we say the series converges to S. Okay? And then otherwise we would say that it diverges. Okay? So again, this is kind of the ideal way to do it, but it's not necessarily an easy way to do it in all cases. So let's look at a couple of other examples here. So let's look at the series where we add the sequence of n over n plus 1. Okay, so we just saw this one as it came out as the sequence of partial sums, but now we're looking at the series of that sequence in particular. So note the difference here. Now, this is our initial sequence of the terms that we're adding. Okay, so we'll look here and we'll say that actually before we do that, I just want to point out, like, if we just think about the behavior of this sequence, right? We know that the inside sequence n over n plus 1, this is going to 1 as n goes to infinity. We just looked at that a second ago. So this means that eventually at the tail end of the series, as we're out at infinity, we're going to be adding 1 over and over again, basically. So we shouldn't expect this to converge, right? We're going to be adding something to the series infinitely. The terms are going to 1, so it's always going to be getting a little bit larger. So this means that we shouldn't expect it to converge. This is opposed to something like this one, where the initial sequence, the 1 over n times n plus 1, this is going to 0. So eventually you're not adding anything to the series, right? At infinity, you're adding 0 infinitely, which is not going to increase the series at all. So that's kind of the idea of when we would expect this to converge or diverge. It's not perfect, because as we saw here, 1 over n does go to 0, but yet it does not converge. And that one's a little more complicated, so that's why we're not looking at that one yet. But just from that alone, we should not expect this series to converge. So let's look at how we could see that. And it's kind of a good idea to have that kind of strategy in mind, whether we're trying to show it diverges or converges. So S1 is equal to 1/2, right? So just 1 over 1 plus 1. S2 would be 1/2 plus 2/3. Okay, and we already got these numbers up above. S3, and I'm not going to write out what these numbers are yet, because it won't actually matter. Okay, so we get 1/2 plus 2/3 plus 3/4. Okay, and it's kind of going to follow this pattern as we go. So what we want to show here is, okay, can we show that maybe, can we establish any kind of inequality here? If you try to just come up with a general sequence for these numbers, it's going to be pretty difficult. Okay. So this is another technique where we try to instead show some kind of inequality that will allow us to say something about the limit. Okay. So in particular, we have 1/2 for S1, that's fine. S2, this is going to be greater than 1/2 plus 1/2. Okay. So in particular, the 2/3 is what's greater than 1/2. And then the other 1/2s are equal, of course. The reason we want to write it like this is because now we can write this as 2 times 1/2. And now this one is greater than 1/2 plus 1/2 plus 1/2, which is 3 times 1/2. Okay, and this one appears 1 times 1/2. So essentially the idea here is like, okay, if we have S4 now, 1/2 plus 2/3 plus 3/4 plus 4/5. Again, all of these are, well, overall at least, this is going to be greater than 1/2 4 times. So we're able to establish a pattern this way. So it's hard to establish a pattern for the terms itself, but we can establish a pattern for something smaller than it. And from that, we can say, okay, then the kth partial sum, this must be greater than k times 1/2. Okay. So because S4 is 4 times 1/2, S3 is greater than 3 times 1/2, etc., right? And we're only trying to say something about the limit, and this allows us to say something about the limit, right? Sk is always greater than k times 1/2. K times 1/2, this is clearly divergent, right? If we just look at 1/2 times k, as the limit as this goes to infinity is just going to be infinity, right? Because it's just a constant times a number, or a constant times that variable. So this is definitely going to 1/2. If this is going to 1/2 and sk is greater than it, or I'm sorry, if this is going to infinity, I should say, and sk is greater than it, then sk is also going to infinity, right? So from this, we can definitively say that sk is also going to infinity, because sk is always greater than k times 1/2, and k times 1/2 is going to infinity. So this is kind of a preview of what we call the comparison test, which we'll look at in greater detail later. Specifically, we can just look at the actual series itself for a comparison. But this is a very common technique with series when we're just trying to show if it converges or diverges. So if it's greater than a divergent series, then it itself is going to diverge, or sequence in this case, right? Okay. So take a little bit of time to really digest the partial sums, because I know it can be a little bit tricky at first, and get comfortable with like the limits and stuff. And we're going to look at a lot of different tests that we can do in regards to these kind of things.